Okay, class, we'll pick up where we left off at, and we're on page 100, and we will be doing the rest of 1-8. It says the first method we'll study is Hamilton's method, which was approved by Congress for use in 1791, but was never actually used since President Washington vetoed the bill that introduced it. Hamilton's method. It says assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. If it does not, assign extra seats one by one to the districts in descendant order of size of the fractional parts in their standard quota. For example, if 3 districts have standard quota 2.93, 4.70, and 3.15, the first extra seat will go to the district with fractional part 0.93. And the second extra seat will go to the district with fractional part 0.70. Now I will go more in depth with this as we go through the problem. Now we go here to number 1. It says use Hamilton's method to apportion the seats for the city described in the class portion of this lesson. In completing the table on the previous page, you've done most of the work already. Cool. Make sure you clearly write out how many seats each district gets. A table wouldn't be the worst idea. Okay, we will look back on the previous page, which shows the table that we actually need to use. So what we need to do on page 100, for number 1, we would need to draw that table. So, in drawing of that table, we will have our districts, and we can label them District 1, 2, 3, 4, and 5. Then next we will have our standard quota. Our standard quota would be for District 1, 2.67, just like it is on page 99. District 2 would be 6.67. District 3 would be 3.42. District 4 is 5.58. And District 5 is 1.67. Next, we will have our lower quota and our upper quota. Okay, now, as we discussed before, our lower quota is just the number in front of the decimal, so it'll be 2, 6, 3, 5, and 1. And when we add these values up, it gives us 17. Our upper quota, as stated back on page 99, all we need to do is add 1 to our lower quota. And that would give us our upper quota. Now, when we add all of these up, this will give us, what's that, 22. So we know, again, from page 99 that our lower and upper quota did not work. So what we have to do now is try Hamilton's method. So the first thing we do with Hamilton's method, we look behind the decimal and see which numbers behind the decimal are the largest number. We don't look in front of the decimal, just behind the decimal. And if you notice, we had 3 that are tied, 67. So that means we're going to add 1 seat to each one of these districts, that District 1, 2, and 3. District 1, 2, and 5. Now, this is what I would suggest you do. The numbers that you know you have to add 1 to, instead of putting a +1 on the lower quota, why not just circle the upper quota? Because isn't the upper quota just adding 1 to the lower quota? So we know we have to do districts 1, 2, and 5. So we could circle these, and we would know that we would include these numbers in our final answer. So now, to determine our final answer, what we would do is this. We would take 3 plus 7, and then here we would still use the lower quota for 3 and 4. which would be 3 and 5. And then we would add this last upper quota value. Now, when we add all of these numbers together, it gives us 20, which means that it actually works. Now, on page 101, we're going to be introduced to the Jefferson method. It says the apportionment method that was adopted by Congress after Washington's veto in 1792 was designed by Thomas Jefferson, and shockingly is called Jefferson's method. It's a bit more complicated than Hamilton's method. It uses what we call a modified divisor. Now, that's going to be very important. The idea to make sure that every district gets its lower quota. We know that won't work in general because usually the number of seats will add up to something less than the correct total. In Jefferson's method, we'll make the quotas get bigger by making the standard divisor lower. Remember, the standard quota comes from dividing a district's population by the standard divisor. So if the divisor gets smaller, the quota gets bigger. Now, just to show an example, we're basically talking about a denominator of a fraction. Let's say we had a numerator of 3. Say both of these fractions had a numerator of 3. This fraction was 3/10. This fraction was 3/50. Now, what we would do, if we put this in our calculator, we could take 3 divided by 10, and that would give us 0.3, and 3 divided by 50, and that gives us 0.06. Now, if you notice here, the numerators are the same, but when our denominator gets larger, our answer gets smaller. That's what they were talking about. Now, it says Jefferson's method. Assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. If the sum of the lower quotas is less than the number of seats, choose a modified divisor that is less than the standard divisor and recalculate the lower quotas. Use this as the apportionment if the lower quotas now add up to the total number of seats. If not, adjust the modified divisor and try again. Okay, Jefferson method ends up being a trial and error process. We keep trying different divisors until the lower quotas add up to the right total. Let's give it a shot. Recall that the standard divisor calculated earlier was 12. It was 12 or 12,000, depending on if you wanted to put the 3 zeros on the answer or not. Okay, now fill in the table below. In each case, get in the modified quota from dividing a district's population by the modified divisor 11. So what this is saying is we're going to take all of these values and divide it by 11 instead of by 12. So our modified quota would be 2.91. It would be 7.27, 3.73, and 6.09, and finally 1.82. Now that's our modified quota. Now we need the modified lower quota. We still just take the number in front of the decimal. So it'll be 2, 7, 3, 6, and 1. Now we will add all of these up and see whether or not this will give us our answer. And that's actually what number 3 asks us to do. It says add up the modified lower quotas. Does this apportionment work? So we will go 2 plus 7 plus 3 plus 6 plus 1. When we add all of this up, this is 19. And the answer would be no. We are still 1 seat short. Okay, now we'll go over page 102. Go to number 4. It says our next attempt will be to bring the divisor we're using. Well, will be to change the divisor we're using. Do you think we should make it bigger or smaller? Why? Okay, we should make it smaller. And the reason is we need to divide by a smaller number to make the result larger. Okay, number 5. It says try again with modified divisor 10.5. Does the apportionment work now? Is it the same as the one we got from Hamilton's method? So now we're going to divide everything by 10.5 instead of 11. So we have 3.05, 7.62, 3.90, 6.38, and also 1.90. So you would take all of these district values and divide it by 10.5, and it will give you these this new modified quota. Now the modified lower quota, again, we would take the number in front of the decimal. Now we would add them up, 3 plus 7 plus 3 plus 6 plus 1, and that equals 20. So that means that it works. So it works. But it also asks us, is it the same as the Hamilton method? It works, but districts 4 and 5 are slightly different than, I didn't leave myself enough room, but you could put down than the Hamilton method. Okay, now it says Jefferson's method was used in Congress until 1842, when it was replaced with the new method devised by Daniel Webster, a distinguished congressman, senator, and two-time Secretary of State. Webster's method also uses modified divisor, but is based on standard rules of rounding rather than lower quotas. So let's take a look at Webster's method. It says assign each district the number of seats by using standard rounding rules on the standard quota. Rounding up if the fractional part is 0.5 or greater, and down if the fractional part is less than 0.5. If the sum of the seats is equal to the number of seats available, use this as the apportionment. If not, modify the divisor and try again. If there are too many seats assigned, use a larger divisor. If there are too few seats assigned, use a smaller one. Okay, class. On page 103, it says we already know from question 7 in the class portion that using standard rounding rules won't work for the apportionment problem we've been studying. That resulted in 21 seats. So we could skip right to step 2 on Webster's method. Since we have too many seats, we should try a larger divisor. Using a modified divisor of 12.5, fill in the table below. So we'll divide each of these values by 12.5, and we will get 2.56, 6.40, 3.28, 5.36, and 1.60. Now the modified rounded quota, we look behind the decimal. If it's 0.5 or higher, then we will round this number up to 1 digit higher. If it's less than 0.5, then this digit will remain the same. So this is higher than 0.5, so this will go up to 3. This is lower than 0.5, this will stay 6. Lower than 0.5 will stay 3. Lower than 0.5 will stay 5. And here is higher than 0.5, so this will go up to 2. Now when we add all of these together, this is 9, 12, 17, this will be 19. So we know this doesn't work. Okay, now 12.5, so this is 19. Now at 12, it was 21 seats. At 12.5, it was 19 seats. So we know our number must be in between 12 and 12.5. So what we're going to do, we're going to use 12.25. But let's read number 7. It says, if all went well, you will find that the number of seats is too low, which means we made the divisor too big. Choose a different modified divisor and try again until you find the apportionment that results from Webster's method. Remember, we know that using divisor 12 makes the number of seats too high. That was a hint. Again, make sure that you clearly write out the number of seats that each district will get. So basically, we're going to try 12.25 because 12.5 makes it too low, 12 makes it too high. So let's try something in the middle. So I had to draw this table because it wasn't provided, and I know it's not provided in your course pack as well. So you could draw your table. Just press pause and draw your table. Now, when we divide all of these by 12.25, this will be 2.61, 6.53, 3.35, 5.47, and also 1.63. Now again, to modify a rounded quota, we look behind the decimal. If it's 0.5 or greater, we add 1 to the number in front of the decimal. If it's less than 0.5, then we would leave the number in front of the decimal the same. So this is greater than 0.5, this would be 3. This is greater than 0.5, this would be 7. Less than 0.5, this would be 3. Less than 0.5, this would be 5. Greater than 0.5, this would be 2. Now we're going to add all of these up. 3 plus 7 is 10, plus 3 is 13, plus 5 is 18, plus 2 is 20. So this works. Okay, now we go on over to page 104. It says, at this point, you might be wondering, what's the big deal? Why so many different methods? Don't they all result in pretty much the same apportionment? Keep in mind that we're working with an example that has 5 districts and 20 seats to be divided up. For congressional apportionment, there are 50 districts, states, and 435 seats. In that case, different methods can result in significant differences. Another interesting note, an apportionment problem of that size requires a tremendous amount of calculation. So it's no surprise that computers are used. But think back to, say, 1842. At the time, there were 26 states and 242 seats, and apportionments were done with no help on the calculations whatsoever. Those guys were pretty smart. In the technology portion of the portfolio, well, we're not going to do that part. Let's take a look here where it says some of the examples below are apportionment questions and some aren't. In questions 8 through 11, write whether each one is or is not an apportionment problem, and of course justify your answer. Okay, with number 8, a school district raises an extra $1.2 million when a levy passes and decides to divide it among all of the schools in the system based on enrollment. This is not apportionment. Now, it also tells us that we have to justify our answer. Since we're dealing with money, a dollar can be divided up. Because remember, with apportionment, we do this method because it's something that cannot be divided up. Now, we move on to number 9. A manufacturing company with 4 locations buys 22 new stamping machines. The plan is to divide them among the locations based on production levels over the last 4 years. This is apportionment. And it's apportionment because a stamping machine cannot be divided up. Just like our seats could not have decimal values, you cannot give someone 0.2 of a stamping machine and expect them to be productive. Now, we go to the last 2 problems of this section. Number 10, it says each day a team of engineers that works for a utility company decides how to allocate power on the grid to various neighborhoods based on past usage statistics. This is not apportionment. And that's because power can be divided up. And last but not least, number 11, each day the manager of a large roofing company decides how to allocate workers to that day's jobs based on the size of the job and the time to completion. So number 11 is apportionment. And the reason being is a worker cannot be divided up. Because you cannot have 0.3 of a worker. And so that is it.